Hello friends, welcome to my home. Today I want to talk about the fundamental theorem of calculus. Now the first thing to remember about the fundamental theorem of calculus is there's two of them, and they're both called the fundamental theorem of calculus. We'll get to that in a little bit. So I want you to understand first what the big deal is and like what the overall idea is, and I introduced this in class, but the idea of what was the point of the definite integral? Why was it introduced? Um, and in essence, we were talking about when we were talking about motion, right? The definite integral was a way of going from a changing velocity uh, to an understanding of an object's position or location. That's what the definite integral was for. That's what kind of we invented it to tie those two together because we already knew how to go from a static velocity to a position. That's with just straight multiplication. The definite integral is a way to do that when it's changing. And we think about that, does that remind us of other situations? And the earlier situations, like we knew from earlier, the first application of the derivative, which we talked about for a long time, was going if we had some function that told you the position of a thing. Taking the derivative in terms of time would get you a function that gives you the thing's velocity. And then, so we knew that taking the derivative goes from position to velocity, but we just said going from velocity to position, well, that's the integral. So in some sense, the idea is that, integration and derivation are kind of inverse relationships. Right? So they kind of, one undoes the other, right? So, um, if you were to take an integral and then take the derivative right back again, you should get back to the same spot. There's a little bit of complications because the first integral I introduced you was a definite integral, which only gives you a single number. It doesn't give you a function. It gives you a number, right? So didn't realize that. Integrals there must be some kind of inverse. How exactly? So, like I said, you get a number from the definite integral. So we know there's this kind of inverse thing going, but like, how does that actually work? And the way it works uh, is done in the fundamental theorem of calculus. All right. So there are two forms of the fundamental theorem of calculus, or two fundamental theorems of calculus. Doesn't really matter here. So the first form, we have you define the definite integral from a to b of some function f of x dx equals the antiderivative of this function at b minus the antiderivative at a. Right? So this is just to say big F is the antiderivative of little f. So antiderivatives, it's a long way of saying like you have a function that if you took its derivative, you get little f, right? So the way to refer to that is antiderivatives. And you tend to actually later we'll just shorten that. We won't even use the word antiderivative at all. We'll just say the integral function, but that's later, right? And this is a fundamental theorem of calculus. But then we also have this fundamental theorem of calculus where if you were to take the derivative of a function that's defined by an integral, right? And so this is saying like this chunk is, and you might see this referred to as an accumulator function. This is an actually very uncommon terminology. So this is something you don't really have to remember very often. It's really just to introduce this setup here. But this is if you take the derivative of a function that, because we have x instead of a constant, uh, this section defines a function with an integral. So if you want to think about that, so if our little f will represent that as some kind of weird squiggle, right? And if you start at a, right, as you move x around, so like if x is over here, our integral function is just this little area. But as you move x away, well, then our function gets bigger. And if you move it this way, our function gets actually negative, right? So it's kind of a way of keeping track of how the area changes as you change the bounds. That's what it's all about. Basically, if you do the integral and get in a way that gets you a function, then take the derivative immediately afterwards, you get what you started, right? You've just happened to have changed variables. Now, so there are two forms, and you'll see in various books, one referred to as Fundamental Theorem Calculus 1, the other referred to as Fundamental Theorem Calculus 2. And doesn't matter which one you learn first. It only depends on the book. Whatever you learn first is the first fundamental theorem of calculus. Whatever you learn second is the second. It does not matter. And more importantly, I forget whether I was going to say something here. More importantly, you can get one from the other. Like if you know one, you know the other. Right. So we'll get into that one. So for example, right, if you accept this one, x equals derivative minus, if you have that as your fundamental theorem of calculus, right, as your first one, then what does the other one become? Well, you have dx of the integral from a to x of f of t dt. Well, you apply this theorem, right? This becomes the derivative in terms of x of the antiderivative function of x minus the antiderivative function at a. Right? That's just a straight application of the theorem. And since we proved it before, we can use it. Well, big F, the idea of big F is that when you take its derivative, you get little f, right? So the derivative of big F of x, that's just little f of x. And then the derivative of big F of a, well, big F of a, since a is a constant, big F of a is also a constant. And the derivative of any constant is 0. So you get just f of x back again. So, and we could do the same for the other way. I'm not going to here because of reasons that I'm going to get to in this slide. The one I call this one the fundamental theorem of calculus 1. And you may notice that I have a preference towards it. So this one I call FTC1. And the reason for that is not only, I think it's simpler to understand, I think its proof requires less to understand, and it is more important to recognize this form. Like this gets way more use. The other fundamental theorem of calculus, you'll see that it basically can only be used as is. Like it can hardly ever be applied. If you're taking definite integrals, you're using the fundamental theorem of calculus 1. All right. and you're going to be taking so many definite integrals. And I just think of it like I feel it's simpler. It requires less overhead. Um, to me, for you it might be different, but it is for them. Um, but yeah, so I call this the fundamental theorem of calculus 1, the other the fundamental theorem of calculus 2. And just this one, you're going to use this one way more. So this one's the one that you need to have burned in your brain. Okay, so let's talk about proofs. Mathematicians like proofs, and that's why they show up in math classes. That's the primary reason. But like, and I mean like proofs in that proofs are how you get more math. So when you have mathematicians, and mathematicians have a big weight in what goes in math curricula, right? They think proofs are important because that's what they do is proofs, and so we include proofs. And I know some classes, a lot of classes, struggle with proofs, not just getting through the proofs, but understanding like what we're supposed to get out of the proofs, because it's not until you've studied math for a while that you even have to remember how to prove any particular thing. But most of the proofs I include to kind of build your memory, to show you how things are connected, right? To try to tie together things or to reinforce concepts. And the biggest thing that we can do to reinforce the biggest concept that can be reinforced with proofs, especially the fundamental theorem of calculus, is the definition of whatever's involved. Now, I'm pretty confident in having drilled the definition of the derivative into my students. And I'll keep doing it because it's still important. But the other reason I like the fundamental theorem of calculus that I prefer is that it doesn't, basically the way the proof has to work is it starts with the definition of something and it gets you to the other thing, right? And the one I like, the fundamental theorem of calculus 1, the definition it uses is the definition of the integral. Whereas if you go try to prove the fundamental theorem of calculus 2, just from first concepts, you start with the definition of the derivative. That's really it. And at this point, we do need to recognize what is an integral at its heart. Because if you keep in your mind what's at its heart, that stays with you. Anyways, we need the definition of either concept, and I told you it's going to be the integral, and then something to bridge the gap. And this is another thing. For the one I like, the thing to bridge the gap is the mean value theorem. Ooh, so this is another chance to review the mean value theorem, which I always appreciate. So let's, at this point, maybe you've already turned off, but if you're interested in a proof, let's do a proof. All right, so the proof of the fundamental theorem of calculus 1. So we're going to start with all our terms defined. So we know that we have a little f and we have a big F. And we know that the derivative of the big F is equal to the little f, right? Okay, so what we're going to do is we're going to start with the right-hand side of the fundamental theorem of calculus, work our way left. So to remember, the right-hand side looks like this. F of B minus F of A, right? So you may remember, and this is a good chance to review, what partitions were. So, you know, we have our idea, we have A and B. So it's like A and B. And so we introduce a partition because integrals are made of summing over partitions. So we introduce our partition where this is x0, and for however many things we have xn, and then there's a bunch of slices. And we'll end up with n chunks, right? Use the partition to slice it up. Now, how do we introduce that into there? Yeah. So how do we introduce that into there? Well, the way we introduce it is instead of having f of b minus f of a, we're going to expand it using the fact that we can always add 0. So if our partition is x sub n for b all the way down to x sub 0, right? F of b minus f of a becomes f of xn minus f of xn minus 1. So the next one, if we want 6 subpartitions, this would be x sub 6 minus x sub 5, right? But this isn't f of a, so we have to immediately add f of xn minus 1, right? We've added 0, we haven't done anything. Well, we can keep doing that. For, minus f of x sub n minus 2 plus f x sub n minus 2. We can just keep doing that all the way down until we get f minus f of x1 plus f of x1 minus f of x0. And we don't need a pair for x of x0 because that was just a, right? So we've taken a very simple difference and we've expanded into as complicated a difference as we want. But more importantly, we haven't changed the value because for everything we subtract, we have to add. Okay. Now, what else can we do? Well, we can always multiply by 1. And this is where we can simplify a little bit. Most things you'll see like simplify so that it's an even partition. It doesn't actually need to be an even partition. The partition can be any assortment of sizes you want, as long as you make it bigger and bigger, the sizes get smaller and smaller. But things are easier for an even partition. So we say the difference between any x sub I and the x sub I minus 1, that's just a particular number, which we're going to call delta x, right? So it's the size of a partition. And we can always multiply by 1. So the idea with our big, huge expansion, we can take our big sum, so f of xn minus f of xn minus 1 plus minus f of x1 plus, or f of x1 minus f of x0. We can multiply that by 1 in our special form of 1 in this case, just for simplicity's sake. Again, you don't have to do this. You can be very more purposeful in this, but just for kicks, we're going to do delta x over delta x. Right? We didn't do anything. But here's the thing. When you distribute this delta x to each chunk, and you distribute this delta x to each chunk, the chunks become an expression for the average rate of change. So the idea of f of x sub n minus f sub x sub n minus 1 over x sub n, this is the average rate of change between x sub n and x sub n minus 1. So like on our partition, right? If all those slices are even, well, the slope from here to here is this expression, right? Well, if you have average rate of change, and if big F is differentiable, so remember big S is differentiable, because it is. You have something average rate of change, mean value theorem applies. That's what ties it to derivatives. We use the mean value theorem. It's going to apply here. So for each chunk, you'll excuse me if I draw fewer chunks in this point. We have n minus f x of n minus 1 delta x times delta x plus dot 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 plus f x of 1 minus f x of 0 for delta x times delta x, right? So this applies, the mean value theorem applies. This has to equal the derivative of f, so little f, for some x in this chunk. And we're just going to call this x n star, because we don't know where it is. And then we have this times delta x plus dot 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 dot. And then this one, so this would be f of x1 star delta x. You could use a c, I guess, for your constant. It's not that big a deal. But wait a minute. This is a Riemann sum. The idea of like taking this, multiplying it by delta x, taking these values, multiplying by delta x, that's the definition. Like, we know that no matter, for any n, we can pick some x's so that the sum of f x, sum from I equals 1 to n of x I star delta x equals big F of b minus big F of a, right? So that works for any n. So it certainly works as you take the limit as n increases without bound of the sum from I equals 1 to n of f of x star I delta x. And that's where we get it. This is just the definition of our derivative. As you take the limit, the sigma smooths out into an s. This delta turns into a d. We get our proof. Now, I just really hope that ties something together for someone out there. And I know it's relatively rare. Not too many people go on to become mathematicians. But, proofs are there to kind of give you the opportunity. I hope they have a bit of clarity. And I find them, I teach them, I like including them because I think that they're beautiful. And I hope someone out there can see the beauty that I see. All right? Well, thanks for stopping by.